For the rest of this section and all of next section, we're going to talk more about linear correlations. But before we go there, I do have one more comment to make about correlation versus causation, and this has to do with observational studies. You'll remember that in section 5.1, we learned about observational studies versus experiments. An observational study was one where you just collected data, in other words, observations on two variables, whereas an experiment was where you had a treatment, in other words, a way of altering one variable and then seeing if it had an effect on the other variable. Now, an observational study can only show two variables are correlated. And remember, correlation does not show causation. So observational studies can never show that one variable causes a change in another variable. And that's one of the reasons experiments are so important. Experiments can actually show, or at least provide evidence, that there's a causative effect between two variables. Okay, with that said, let's go on and talk some more specifically about linear correlations. There's something called a linear correlation coefficient that gives us a way of quantifying, or you could perhaps say measuring, how linearly correlated two variables are. In other words, is there a linear correlation? And if so, how strong is it? Now, this is going to tell us nothing whatsoever about non-linear correlations. So just because this linear correlation coefficient tells us that two variables are not linearly correlated, doesn't tell us anything about whether they might be non-linearly correlated. Here's the formula for the linear correlation coefficient for sample data. That coefficient is called R, and the way it's calculated is you take the product of the z-scores of both variables for each individual value of the variable, you add up those products, and then you divide by the sample size minus 1. And I'll just remind you what the z-scores are. The z-score for some x value is that x value minus the mean of the x values divided by the standard deviation of the x values. So z-score gives us the number of standard deviations from the mean of a value for a variable. And we talked about that and illustrated it pretty extensively back in chapter 1, so you might want to take a look back there. Let's see an example of computing the linear correlation coefficient for a set of sample data. This is going to be pretty involved, doing it by hand, so I've kept the data set really tiny. It's so tiny that it's almost silly to do this, but if it was bigger, we just wouldn't be able to do this by hand and see an example of using the formula. So here we go. In our formula for R, we need to know the z-score for each of our x values and each of our y values. And to calculate the z-score, I need to know the mean of each of the variables, and I need to know the standard deviation of each of the variables. So that's where I'm going to start. And I think this is kind of a good review of computing these and what they are and how they work. So to start off with, I've set up the type of table that we used in the past for computing standard deviation. So we'll fill that in. I didn't put the formula in for the averages. I didn't put the formula in for them because I'm hoping that we all remember that you compute an average by adding up the numbers and then dividing by the number of numbers. So for x equals 1, 2, 3, for x equals 1, 3, and 5, we're going to go 1 plus 3 plus 5 and divide by 3, and we will get 3 if you do that. For y, we'll go 4.1 plus 7.6 plus 8.1 and divide by 3, and we'll get 6.6. Now I need to subtract the mean from each of the x values. And by the way, I went ahead and typed out the standard deviation formula below this table because I'm thinking we don't all remember that. So in the standard deviation formula, you'll see that in the numerator, under the square root, in the numerator, we have a bunch of x minus x bar squareds. So usually the next column in the table is just to compute x minus x bar. So in the first row, I'm going to have 1 minus 3, because 3 is the mean for the x's. So 1 minus 3, which is negative 2. Then in the second row, I'm going to have 3 minus 3, which is 0. And in the third row, I'm going to have 5 minus 3, which is 2. In the next column, we square each of those. So negative 2 squared is 4, 0 squared is 0, and positive 2 squared is 4. We need to add those up. Why do we need to add those up? Because in our standard deviation formula, under the square root in the numerator, we have the sum of the x minus x bar squareds. So adding those up, 4 plus 0 plus 4 is 8. At this point, we can compute the standard deviation for the x variable. Under the square root, we have the sum of the x minus x bar squares, and we just said that worked out to be 8. Our sample size n in this case is 3. We have 3 pairs of data values. So I'm going to be dividing by 2. Well, I don't even need a calculator for this one. 8 divided by 2 is 4, and the square root of 4 is 2. So that's the sample standard deviation for the x values. Let's do the y values now. My first y value is 4.1. I'm going to subtract the mean of the y values, which was 6.6, and we will get negative 2.5. Going on, the next y value is 7.6. If I subtract 6.6 from that, I get 1. And the last y value is 8.1. If I subtract 6.6 from that, I get 1.5. Then for the next column, we square each of those. So negative 2.5 squared, that's a positive 6.25. Then we have 1 squared, which is of course 1. And last we have 1.5 squared, which works out to be 2.25. Then I add those up, which is going to give me 9.5. So for the standard deviation of the y's, we have a 9.5 in the numerator. Again, we have a 2 in the denominator. And running that through a calculator, we'll get about 2.179.